The next speaker, Petrov Eugene Vyacheslamovich, Vasil Nazarovich Karazin, Kharkiv National University, talk about constant mean curvature surfaces with harmonic Gauss maps in three-dimensional Lie group.
Hello, and let me thank the organizers for an invitation to give a talk and for this wonderful conference, for organizing it in such hard times. My talk is devoted to the Gauss map of surface and three-dimensional Lie groups. And it's based on joint work with my former student, Elena Savchuk. So usually when we define a Gauss map of a hypersurface, say in Euclidean space, we talk about parallel translation. So we take a normal vector or maybe a normal subspace, a line at a point of a hypersurface, and we translate it to the origin. So this is a classic definition. So if this hypersurface is immersed, we will talk about immersed smooth hypersurfaces. If it's immersed in a Lie group, then we have a natural notion of left translation. So we can use this left translation to define the Gauss map. So if we have this hypersurface M, and we can define the Gauss map phi from M to the projective space RPN by this formula. So we can take a normal line NPM and apply to its differential at the point of a surface of a left translation of the left translation in this Lie group L p to the minus first degree. We get one-dimensional subspace of its Lie algebra, and the set of such subspaces is naturally identified with RPN. And if we have an oriented hypersurface, of course, we have the unit normal vector field, two fields depend on the rotation, and so we have we may translate this normal vector, unit normal vector, and get an element of the unit sphere in the Lie algebra. So we get a Gauss map to SM. Here we are concerned with harmonicity of this map. Let us recall what are harmonic maps. So the basic definition is as such: if we have a map, smooth map, yes, from compact Riemannian manifold to some other Riemannian manifold, we can consider the function of energy. So it's an integral over M from this function, the trace of the codifferential of the second matrix with respect to the first matrix. It's a variational problem. Its stationary points are called harmonic maps. As usual, we can write down the Euler-Lagrange equations. Here, they have the following form: the trace of the second fundamental form of phi equals 0. Here, the second fundamental form is more or less obvious generalization of the second fundamental form of a submanifold, and this field is not normal. No, it's a section actually. It's a field of on M with values in Tn, this field is called the tangent field of phi. And using this field, it's well defined, of course, also for non-compact M. So we can simply define the harmonic map if this field for this map equals zero. We can even define the harmonicity at a point in such a way that we can do it, say, minimality when at this point this map equals zero. And in particular, it's well known that the map to the Euclidean space, is harmonic if and only if its coordinates functions are harmonic with respect to the Riemannian Laplace and with respect to the usual Laplace-Beltrami operator. And so this partially explains the name. And also the map, if the map is to this n-dimensional sphere in the embedded, standardly embedded in En plus 1, then this map is harmonic if and only if this coordinate-wise Laplacian of this map as a map in En plus 1 satisfy the following equation. Number GFA for each A equals -2 to the energy density function of phi multiplied by phi A. So it's a criterion for harmonic maps into spheres that we will use. In fact, not only for maps into spheres, but only for maps in projective spaces using the usual universal covering. And the usability of Gauss map for differential for studying differential geometry and mean curvature of hypersurfaces in Euclidean space is connected in part with the following fact. The theorem of Rouen-Wilms, that the Gauss map of connected hypersurface is harmonic if and only if the hypersurface is of constant mean curvature. With respect harmonic with respect to the standard metric of constant curvature on RPN or SM. So there is nice generalization of this fact to our left invariant Gauss map that was introduced at the beginning. This map is harmonic for a hypersurface in a Lie group with a bi-invariant metric. So the metric that is not only left invariant but also right invariant, if and only if M is of constant mean curvature. So it's a straight generalization. It's true for hypersurfaces in En+1 in SO3, or if you wish, in its universal covering S3 with metrics of constant curvature. I don't want to talk here about higher codimensions. Of course, the theorem of Rouen-Wilms is true also for higher codimensions, where we talk not of CMC hypersurfaces, but of submanifolds with parallel mean curvature. But for left invariant Gauss map, I showed that some time ago that it's not true even for bi-invariant metrics and even for totally geodesic submanifolds. So we have examples of totally geodesic submanifolds with non-harmonic map for higher dimensions. In higher dimensions, we of course we map not to the projective space but to the Grassmann manifold in the same fashion, but to the Grassmann manifold. Okay, and in general, general, for general left invariant metrics, this the analog of Refilm's theorems does not hold, and this is the example that I investigated some time ago. This is the hypersurfaces in the 2m+1 dimensional Heisenberg-Lie group. So we can describe this as the space R 2m+1 with the following basis of left invariant fields that have non-zero brackets of the form xy to the yi equals z for such fields. And if we, well, the usual, the standard left invariant matrix is such that this is an orthonormal frame. And for such metric, if we have CMC hypersurface with a harmonic Gauss map, then it's vertical. So the field Z is tangent to it. If it is complete hypersurface, then it's simply a cylinder over a constant mean curvature hypersurface in the Euclidean space. So not only we don't have in general the equivalence between these two properties, but their simultaneous when the simultaneous take place, we have very restricted conditions. We have very narrow class of relatively narrow class of hypersurfaces. In particular, if m equals 1, so it's three-dimensional Heisenberg group, usual Thurston geometry. And then the surfaces are vertical Euclidean planes, vertical in the usual sense, so parallel to the z-axis, and vertical Euclidean route cylinders. And so let us give some technical results that I used in the proof. Here it's in the form for a surface in three-dimensional group, because this is the case that will be considered in today's talks. So we have a surface in three-dimensional Lie groups with the usual notation for its Riemannian metric, Riemannian connection with a tensor. In some point P of M, let's consider an orthonormal frame y1, y2 of the tangent plane. Some are the usual notations for second fundamental form of the mean curvature. Y3 is a unit normal vector at this point, and we can continue these three vectors by left invariant fields. So we can note on M, so it's in a sprint on G. That we can continue by a field defined on G. And so we can, in particular, compute covariant derivatives of these fields with respect to another these fields. So here the covariant derivatives in the sense of the Lie group. So we have the next criteria. So the Gauss map is harmonic at P, in the sense that the tangent field vanishes at P, if and only if the following conditions for y for j, sorry, equals 1 and 2 hold. So it's some conditions that well, include the geometry of G, some geometric structure of G, and the external geometry of M. Some characteristics of external geometry. And for a three-dimensional Lie groups, of course, we can use very well-known description by Miller, very well-known and very widely used for different problems. So let us recall that if G is unimodular, so it's for connected groups, it's equivalent to the traces of its adjoint operators vanish. Then there is an orthonormal frame with the following Lie brackets for some set of coefficients. And we can rewrite this criterion in terms of this coefficient. But in the general case, it's quite messy, so I will not show you this in the general form. But for some particular cases, it's more pretty. First of all, when all lambda I is equal, it's simply the case of bi-invariant metric. It realizes for E3 when they vanish, and for SO3 or S3 when they are non-zero. And in this case, this formula simply have this form. So really, we have that. Indeed, we have that phi is harmonic if and only if the surface is of constant mean curvature. Let us consider the case when 2 of lambda I is equal and the third is different. So let us denote them by lambda and mu. Algebraically, that means that adjoint operator is Q-adjoint only for x proportional to E3. So the metric is right invariant with respect to a one-dimensional subgroup, not for with respect to all Lie group, but for the corresponding one-dimensional subgroup. And then the formulas become like this. So here we have alpha, that is the angle between the normal vector at the point and the vector E3. So we have some distinguished direction defined by E3, and we are able to prove the following. If in this situation, from any two of the following claims, the third follows, that M is of constant mean curvature, that the Gauss map of M, phi of M is harmonic, and that M is either everywhere orthogonal to the one-dimensional foliation generated by RH, it's natural to call it horizontal, or is composed of leaves of this foliation of the integral curves. So it's natural to call it vertical. So it's easy to see well, from where it follows. For horizontal and vertical surfaces, sine of 2a equals 0. So a is 0, or p over 2 of odd or pi. Yeah, pi over 2 or pi. So we have that situation. Yeah, we have that criterion of the constancy for h. So we have equivalence between claims 1 and 2. And if claims 1 and 2 holds, yes, we can assume that claim 3 is not true. So at some point, sine to alpha is not 0. And this allows us to find coefficients of the second fundamental form. And then we use some equations of the submanifold geometry of submanifolds, namely the Kodats equations, and we are able to come to a contradiction. So this is the idea of the proof. What cases are they? So if lambda equals 0, mu is non-zero, this is a three-dimensional Heisenberg group, and this is a case considered earlier. Note that in this case, there are no horizontal surfaces because the orthogonal distribution to E3 is not non-integrable. If lambda is non-zero and mu is 0, it's a group E2 of orientation preserving Euclidean plane isometries. It's a solvable group, so its universal color is simply R3, and in fact the metric, the left invariant metric, is Euclidean. And so it's a Euclidean space, but with non-standard group structure, and so non-standard Gauss map. And this Gauss map is not very good because connected complete CMC surfaces with the harmonic Gauss map is only Euclidean round cylinders or vertical or horizontal Euclidean plane in this case. If lambda and mu are non-zero of different signs, it's the case of a cell to R. And here we can give a corollary for the standard metric on the cell to R, namely for lambda equals 0 and mu equals minus, lambda equals 1 and mu equals minus 1. So it's a standard Thurston geometry, as you heard from Igor already. This is also the universal covering of the unit tangent bundle of the hyperbolic plane with the Sasaki metric. And it has the following model. Of course, we can obtain it from the half-plane model of H2. And in particular, the basic fields are as such. So the integral trajectories of E3 are again vertical straight lines, and the orthogonal distribution is again non-integrable. So we again have round cylinders or parts of cylinders because we have y more than 0, or vertical Euclidean planes or half planes. So it's simply cylinders over the curves of constant curvature in H2. H2. And for non-zero pairs of the same sign, we give some non-standard left invariant metrics on S3 without constant curvature, and we have the same type of results in this case. For the case of pairwise different lambda I, so this situation is messy, and well, we can give only some examples, so no general statements, but we can compute harmonicity for some examples. For example, for the group Sol3, for the solvable group, again with the standard structure, when lambda 1 equals 1, lambda 2 equals minus 1, lambda 3 equals 0, we have the following basic fields. And for example, we can use some existing examples of minimal surfaces, or we can consider again Euclidean planes, and for example, z equals 0 has harmonic Gauss map, but it's minimal. But the total geodesic surfaces x equals 0 and y equals 0 have non-harmonic Gauss map. And finally, for non-unimodular case, we have again due to Milnor the structure of this form. So we have a normal frame with the following brackets for some real lambda and mu, and here. Again, we can get some pretty messy formulas, but here one of the interesting cases is, of course, a case of hyperbolic space, of the Lie group structure on the hyperbolic space. And this is a case when lambda and mu vanishes in these formulas. We get a half space model of H3 with the usual metric. We get this frame. This is from of the basic left invariant fields, and we have the criterion for harmonicity takes this form. So we again have some terms of so external geometry, some second fundamental form, and also we again have the angle between Y3 and E3. Let's call that E3 is the vertical direction. It's in the vertical direction again. So this allows us in the same fashion to prove the following theorem: completely connected surface in H3 is CMC with a harmonic left invariant Gauss map if and only if it's for a sphere of the form z equals z0. So it's for a sphere parallel to the sphere at infinity. So no, we can see in this case sine alpha is 0. So again, it's this situation, and if sine alpha somewhere is not 0, we have expressions for the second fundamental form, and we can come to a contradiction. Well, this indicates that this Gauss map is simply not very suitable for surfaces in H3. So the left invariant, the Gauss map that is connected to the Lie group structure is not very useful for its geometry. In fact, there are other definitions of different definitions of Gauss map in H3 that are better in this department. So they allow the partial, not in the full form, but in partial forms, they allow Rouvium's type theorems. Okay, thank you.
Thank you very much, Evgen Vячеславович.